See you Thursday.
Okay, guys, let's get started. I don't know if there's an AV system in here. I guess everybody at the back can hear me okay, yeah? Excellent. Cool. Yeah, so rainy day. That was fun. Today's going to be the first day that we're actually diving into the material. So if you go to, you guys all have the course textbook at this point? Should I put it in the chat? I'll put it in the chat, and maybe I'll put it on A2L every week so that everybody has it. But it's here. MintLab, GitHub, IO, NFIS 3 and M4. You know, you could just read off there. That's okay. Okay. If you do want to launch it in Google Colab, what you have to do is go to the rocket ship icon, go down to Colab, and if you're logged in on a Gmail account, it's going to take that sheet. That sheet is actually an interactive Python, what do you call it? Jupyter notebook, right? And it's going to load that up in there, and everything should actually run if you just hit run all. Yes, it's okay. I promise I'm not going to try and steal your data. Right? And then it's just going to go through, and that's going to run, and it's going to execute everything along. So all of the codes that are in there are generated in line. That's one of the advantages of doing it this way. So you can go through, and if you have any, you know, hey, what would happen if we're going to start talking about like round off errors, right? So if you're worried about, okay, what happens if you use some other number or anything like that, go in through Colab. You're going to have to run it all because it contains the import statements and things like that at the top. But then you can go in and fiddle around with things and like actually get your fingers dirty with it. Okay. But in the meantime, no, not that. Oh, that's going to be fun. Okay. I kind of prefer teaching from the textbook view just because it's a lot cleaner. And I find the formatting a lot more appealing. But the Colab view is also fine. Okay. So round off errors. What we're going to talk about this week is in the 2 remaining days. It's a short week. How numbers are represented and how functions are calculated within computers, right? Has anybody here done binary algorithms somewhat, right? Mr. President has. So we're gonna touch a little bit on that. This isn't a course on binary, octal, hexadecimal. We don't have to worry about that stuff. But there are going to be some kind of interesting things that you should be aware of when you're using these larger codes. Okay. So round-off errors are unavoidable because we're representing things in finite precision, right? So when we write the number 1, right, we know that that is the number 1. And we could say there are an infinite number of zeros after that, right? That is a symbolic representation. It's an object, not necessarily a number. Computers don't always represent numbers in that way. Typically, what they would do is say, okay, well, you have this, you have a certain number of significant digits, and you don't care about anything on the other side. And the problem is that if there is stuff that's hidden, literally, on the other side, when you're doing these numerical algorithms and you're multiplying this by 10 and 20 and 30 and 40 and 50 and 60 and 70, you know, algebraically and symbolically, that should always be 1, right? But if you keep doing this and doing this, all this gobbledygook at the end here can accumulate and it can take down your systems. Right, so this is one of the ways that the people can design robust numerical algorithms. COMSOL, again, for those of you returning from last year, COMSOL has all this stuff kind of built into it already, so you don't have to worry about it. There are some occasions when you would see something like this, and we'll touch on that with the subtractive cancellation on the next slide. But generally speaking, a lot of these algorithms are built specifically to avoid this, and I'll show you guys how it works. Okay. The issue is particularly prominent with irrational numbers, obviously, right? 3 is exactly, or pi is exactly 3, right? I saw the Simpsons reference, thanks to Willow. So I don't know if you guys remember, this is probably like 10 years before you guys were born. There's in a big science convention, Professor Frink is there, and all the scientists are blah, blah, blahing, so he upsets them and saying, pi is exactly 3, and everybody's like, oh. But then, anyway. And the engineering joke is that pi is 3. And that just pisses everybody off, right? Of course, there are other irrationals. E, square root. E is all over the place in physics because it's the function for Arrhenius equation, right? Exponential decay for those of you guys going into to nuclear, right? So and worse than that, it's actually raised to a power, right? So you've got e to the power of 1.73, right? And now that gobbledygook at the end can kind of start to creep in and mess around with things if you're not careful. Okay, so these are, again, some things. If you do run the Colab file, you can just execute these and it'll spit this out. There are formatting instructions to show you more significant digits than just this. This is kind of the normal view of precision here. If you go in farther, and I'll show you that on the next slide, then you start to see all the gobbledygook at the other end. Okay. Really, the problem is that that we can only. So the way that it is normally stored is something called finite precision, and it's quite literally the number of digits that you're storing in memory, right? So this goes back to the fundamental ways that computers are storing numbers. They're not concepts; they're actually data within a register, right? And whether or not those registers and those memory things are activated, 1, 0, we're into binary, right? But there's only a certain number of those, and therefore you can only represent numbers to a finite precision. That's where the name comes from. Here's a great one that comes back to haunt me. The average human is capable of roughly 1 mistake a minute, 1 mistake a second, but computers can make billions of mistakes a second, which is fantastic. And now you have multi-core, high-performance computers. You can just make errors till the cows come home, no problem. Yeah. So if we had an infinite number of digits, if we could just keep writing and writing and writing, there wouldn't be a problem, right? 1 over 3, 0.333333333, right? Conceptually, we know that times 3, right? What's 1 over 3 times 3? 1, right? Computers aren't going to give you that all the time, right? Because it's not representing 1.3 repeating infinitely. It's representing 1.3 8 times and then cut. Well, 1.3 repeated 8 times, then cut and multiplied by 3 is not going to give you back 1 unless you round it. Right, and that's where kind of the algorithmic and the numerical robustness comes in to help you out there. Anybody use Mathematica, Maple, Python, SymPy capabilities? I see a nod of nods. Any of you guys know what the big differences are there? Yeah. Do you know what that means? Yes. Yes. Yeah, effectively, right? So it keeps the symbol, in which case 1 is actually 1, right? And it knows algebra, so that 1 over 3 times 3, the 3's cancel out, and you get 1, right? Anybody know the big problem with it? Why we don't do something like COMSOL in Maple or Mathematica? You already answered one. Come on, I know it's like 8:30 in the morning. Don't make me start asking questions. Somebody from the back here. Nobody? I'm going to start calling names. Brown shirt. Scratched our eye at the wrong time. Why do people not use something like Maple or Mathematica that's really good at math for like the big math equations? Yes, absolutely. Right? Because that expression tree, and it is a tree, that's the way it works, right? It's all built on binary operators. You make a binary tree, right? But then you do that and you square it and it gets longer. And you multiply it by another equation and it gets longer. And these things get long and long and long and long and long. And even the act of simplification is itself tremendously painful for these computer systems to do. When it comes to actually evaluating things, so I don't know if Maple and Mathematica are, yeah, I'd be surprised if they don't have these tools yet. I think MATLAB was doing this with their symbolic logic. You export it in SymPy, it's lambdify, I think the function is, right? And it's taking your symbolic equation and it's making a normal algebraic equation out of it. Sorry, algebraic function out of it, right? So what that's doing is it's collapsing that whole symbolic logic tree and putting it into like kind of a standard finite precision type function. And all of a sudden it evaluates much, much faster, right? That's the benefit from all this. If you have 1 over 3 times 3, super simple, right? If you have a quintic polynomial that you would need to factor, and you've got another quadratic on top, and it's one of the terms is the same, you've got to factorize that, you've got to cancel that. It gets longer and longer and longer doing that sort of thing. So that's the main benefit for moving to the finite precision stuff is the speed and also the what would you call it? Let's go with evaluation, right? If you have, trying to think of a good example for this one. If you are writing equations that maintain the symbols and you have two or more constants, right? So say you had an Arrhenius equation. Say you had 2e to the negative 3x, right? Computer isn't calculating e to the anything x. It's doing a Taylor expansion. We'll talk about that on Friday, right? Well, guess what? That prefactor in front of your exponent and that factor inside your, I thought I just had a whiteboard marker. Say you have 2e to the negative 3x, right? It's not calculating this. It is calculating, I don't know the Taylor expansion of exponential off the top of my head, right? But what you're going to get is 2 times blah, blah, blah. There's probably a 1 here, a 3 here, a 9 here, you know, n to the powers, right? Blah, 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 blah. When you compile this stuff, you can do all this multiplication beforehand. So you don't need to do 2 times this. You can do 2, 6, 18, yada, yada, yada. And that, you know, simple example, obviously not the biggest case in the world, but as you build up your functions larger and larger and larger, that does become important. COMSOL actually maintains symbolic representation until the point where it's assembling the matrix. Matrix assembly is week 12. Won't get to that one when we talk about finite element for a long time, right? But if you do differentiation, I don't know, did we talk about diff function in COMSOL? Doesn't matter, right? If you do the diff function in COMSOL, even when it's calculating the Jacobian, again, we're going to talk about that one, it's actually doing that symbolically, and that was actually one of the, probably the biggest change that COMSOL brought to the market, was being able to calculate that Jacobian symbolically. But again, we'll talk about that with Newton's method. Okay, finite precision representations. So this is one of the longer ones. Again, Colab will launch it. Binder, we're still playing around with. Same with live code. I wouldn't rely on that. I'm not going to recommend that right now. I would go with Colab if you are going to execute it in time. Okay, binary. Anybody know about bases? Bases. I see some nodding heads, right? So we use base 10, right? Decimal. Base is 10, right? Decimal system is the base 10 system. Except apparently for the Mayans, which is kind of neat, they apparently use the base 20 vetesimal system. I guess they were counting on their toes, hands and toes, right? Because this is, I'm fairly certain, having not actually looked up and like researched this seriously, I'm fairly certain this is why we have decimal system. But anyway, right? So in the decimal system, and anybody who's done binary is this is going to be a little bit of a refresher, right? In the decimal system, each digit's position corresponds to a power of that base, right? So you've got the number 1305, that is 5 times the base 10 to the power of 0, plus 0 times 10 to the power of 1, 3 times 100, 1 times 1,000, right? You add those all together, and lo and behold, you get 1305. Great. Computers use base 2 binary, where each bit can either be a 0 or a 1, right? So the same number is written as something that looks like that. And if you wanted to convert it back, then you would have to repeat that procedure, right? You go 1, 2 to the power of 0, power of 0 is 0, is 1, 0, blah, 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 and lo and behold, you get back 1305 in base 10 representation. Some people will use this subscript here, 210, to denote the base. It's especially frequent in logarithms, right? Logarithms are all about this base conversion stuff, right? So you'll see that a lot. Anybody into quantum computing? So originally, I thought that, so quantum computing is all about like qubits, right? And I remember that qubits can, somebody like jump up and correct me if I'm wrong, because I remember that qubits can assume one of 4 states, but their representation is beyond just like the power of 4 versus 2 states, something like that. If anybody is into quantum computing and they want to do this as an independent research project, Absolutely. I'd love to learn more. Right. So talk about how it's represented, how the algorithms work. I know there's something about superposition, like, and its effect on algorithmic efficiency, blah, blah, blah. Like, anybody wants to look into that? 100%. Absolutely. Come and talk to me first, and then we'll repeat that to Peter, and then go for it. That would be really cool. Okay. Binary representation can also include fractional parts, right? Same way that we would use a decimal point. So it's easy enough to go 10 to the power of 0, 1, 2, 3, 4, 5. We can also go the other way, -1, -2, -3, -4. This is a function that will convert the decimal function, what do you call it, the fractional function, right, into the binary equivalent. I'm not going to go through the algorithm to get this because it's kind of more electrical engineering, to be honest. So I'll just skip to the good stuff here. Okay, so in this case, 54.75 as a representative problem, right? In binary is this, right? 0.11. And you can check that doing the exact same thing, right? So that's 1, 2 to the power of 5, 4, 3, 2, 1, 0, -1, -2, and lo and behold, you get the same base 10 thing. Anybody want to try converting 0.1 to binary? Nobody? It is not. Ooh. Yeah. I thought that too, but no. Because of the way that the fractional system works, it actually turns into this funny guy, right? Because so, right, the 1 would only work if it was 2 to the power. So because it's 2 to the power of -1, that decimal point, right? 2 to the power of -1 is what? 1/2, right? So that's going to be 0.5, right? Because it's tricky, right? It's not just 2 to the power of 0. It's actually 0.5, and then you have to subdivide that and subdivide that and subdivide that, and you end up getting this funny number here. It's tricky. This is a great example when I heard about this the first time because it's insidious. This is actually non-terminating, non-repeating. This is equivalent to saying 0.33333333. So even something like 0.1, which honestly, what the heck, right? Like, it's insidious because you would assume that it's super easy, and then you actually go and do this, and it's not. And we're going to see why that's important in a second, right? Okay, just before we jump into some more of the interesting things, let's talk about precision a little bit. Computer stores data in units called words, right? The number of bits in a word determines the precision. Okay, there is the IEEE created these standards for floating point arithmetic, and it defines the following. Single is 32 bits, double 64, quad precision is 128. We'll come back and we'll talk about exactly what that means. Just for reference, the representation of 1305, right? This number requires 11 bits, but you can't just have like a variable number of bits for every single word. It's just not algorithmically efficient, let alone like just scheduling and finding places for all these memory things, right? So what you would have to do is you would have leading zeros, or you would use floating point arithmetic, which is later on. I lied a little bit. There are Python packages that will allow you to go to variable numbers of precisions. I forget what it's called, mathf or something like that, right? But then that's a wrapper on top of these things that'll let you go out as far as you want. Guess what? Infinity is still going to be too big for your computer. So the pros and cons of this are up to you. Yeah. Yes, asterisks. Yes. So yes, that statement is exactly correct, but you're going to see in the floating point precision that the different chunks within that word are going to mean different things. And that kind of extends that, like engineering notation. Cheat, spoiler alert, engineering notation allows you to get much larger than you would normally get. forget if I mentioned this later. Yeah, no, I think I did. Never mind. Okay. Any questions so far? We'll go on to the next ones. Cool. Integers. Fundamental data type for signed numbers. They do not suffer from round-off error. Anybody know why? They're not what? Well, I think you already answered it earlier, right? With the 0.1 thing, right? The fractions get messy, right? Everything else, as if that 0.1, even the simplest case, was on the other side of the decimal point, wouldn't be a problem, right? You can go up by increments of 1, which is exactly what you want in order to have like completeness of the entire number set being able to be represented, right? It's the fractions that make things kind of messy to do this sort of stuff, and with surprising consequences like 0.1 converted. Let's see. They do have a limited range based on the number of bits used for their storage. So this is where the precision comes in, as you'll see in a second. Okay. The range of values that it can store are determined by 2 to the power of bits, right? So if you have 32 bits, right, the largest number is going to be 2 to the power of 32. And then whether or not you include 0 is another question. So maybe it's -1, depends on your representation. And the range is generally split between positives and negative values. So a lot of the older programming languages will allow you to define data types. Is this just out of curiosity? Have you guys heard of like actually defining data types in your codes? Okay. With Python, you can, but you normally wouldn't, right? Because it's just kind of like the general thing. Same thing with MATLAB. It has the general matrix class, right? C++, if anybody's done that, Java, at least 20 years ago, last time I did C++, right? You had to define that it was float 32 or integer or whole, right? Because a whole number is the same as the integer without all the negative stuff. So if you're doing something like a counter, you will never get to negatives. But by ignoring that entire side of the number line, you can go twice as far into the positives, right? Which can be beneficial. Modern computer systems, I mean, 2 to the power of 31 is still a really big number. If you have a counter that's going past 2 to the power of 31, I think I actually have it here. I know. But like if you have a counter that's going up past that, generally you want a more sophisticated counter anyway, but they still have it. Okay. Due to the representation, so the range is determined by 2 to the power of your precision, right? For assigned integers, the range is divided between positive and negative. And due to the 0 being in there, it's actually favored towards the negative side. So you can technically you can represent more negatives than positives by 1. The minimum value is -2 to the power of, I think I have it here, right? And the max is same 2 to the power of that -1, right? -1 because you're dividing that thing by 2, so that means in the exponent you get -1, right? And then you take away 1 there. Modern computers use a method called 2's complement, right? That avoids having to use a signed bit. So with floating point precision, the first bit is going to be your sign, positive or negative, right? For integer representation, they don't do that. The integers, the way that they're stored in binary is using this 2's complement method. And the reason they do that is because then the algorithm for working with those things in binary, not decimal, exclusively in binary, is through this, is the same for positives and negatives, and the algorithm applies in both cases. We're not going to go into that. That's not what the course is about. Okay. What's the largest integer a double precision variable can store? How many bits in double precision? Okay. So what? Yes. Yes. For the positives, it's 2 to the power of 64 minus 1, so 63. Can you guys see this okay? Do you want me to turn off the lights up here? Next question, how do you turn off the lights up here? I don't know if that made any difference whatsoever. How's that? Is that okay? Cool. Just remember that one for next time. Okay. Right. And then, so does this make sense to everybody? And you can see that the minimum actually goes all the way out to 8 on the last part here, and the max goes out to 7. Does that make sense to everybody? Does this not make sense to anybody? All right, cool. We can check it with the built-in NumPy examiner, right? And this is just one of these things that'll dig up the documentation for this and help you out with, like, the representation. Honestly, at this point, like, hey, Gemini, what is this? Or like Google, Stack Exchange, Wikipedia, all this stuff has it, right? But we can check it, and sure enough, yes, we do get that. So what happens when we do something too big? Anybody have a guess? Not the people no, somebody new. That'd be somebody new. Yeah. You get an error, yes, right? So if you try to say, right, print this number int 64-bit integer, double precision integer, right? 2 to the power of 62, that's fine. But 2 to the power of 63, not 2 to the power of 63 minus 1, but actually 2 to the power of 63, you're going to get an overflow error, right? And then you're going to see some gobbledygook that says, and it says to convert to C long, and now we're into like the underpinnings of what Python and Cython, CTHOYON, right? Like that, what that underpinning is doing. So Python is a computer science guy. As I recall, Python is more of an interpreter. It sits on top of like the C engine underneath, which is why it's actually still reasonably fast, right? And the C version of Python is Cython, Cython, right? But here you get to see like a little bit of the gobbledygook inside it. If we want to do something else, like for example, this guy, convert this to integer 64-bit, no problem. And this one also comes up with an overflow error. Would you ever write this number down? Right? So I wrote these notes last year, and yesterday I was going through and I was staring at that number and like, this number is meaningless to me, right? Like, I'm just going to write it out in engineering notation because that makes a whole lot of sense, right? Is that, yeah? How many people right now are like counting the zeros, right? Engineering notation is precisely floating point numbers. But before we get there, I do want to tell a very quick story. Apparently, overflow errors. So C's, like the C programming language checking for overflow error is a result of hacking, evidently. Because what people would do back in the day is they would use, so when you overflow, the original way that it worked is it tried to convert that number into like the memory registers, right? And as long as the number was below that the max integer, it could do that, no problem. But if you put in a number that was too large, then it would literally overflow that memory block into the one beside it. Now you have a problem because you have contaminated that block. And hackers used to be able to exploit that to gain entry into computer systems. Isn't that wild? Right? Like just knowing where these blocks were, you could literally overflow one into the other one so that you would get access into some forbidden part of it, or corrupt it and break down like security checks and stuff like that. So this is actually like C doing a check and saying, hey, is this number too big? If it is, then reject it, as opposed to just like trying it and not doing it, specifically because of hacking attacks that were successful with this. I think it's overflow registers, I think is the type of security vulnerability that's all about this. Just kind of a neat, like oh, hey, it's kind of weird. All right, so nobody would ever write out a number this big, right? It's much more efficient to use engineering notation. It's just, I read a book a long time ago called Innumeracy. Talks about like people's inability to even understand what number this big looks like. And I'm running out of time. Somebody, if I finish this lesson on time, somebody remind me about the 10 trillion seconds, okay? I'll try and get through because it's a really funny exercise. Okay. Floating point decimal numbers. I'm going to speed up so we can get there. Okay. Engineering notation, right? We remove leading and placeholder trailing zeros. So 1 with 19 zeros after it, not very useful, right? Let's get rid of the 19 zeros after it and just say 10 to the power of 19 or 1e19, where e is understood to be 10 to the power of, right? In which case, right, everybody knows engineering notation at this point, right? Right? Good. If you don't know engineering notation, get out. You fail. Okay? There is a little trick because 1500, right? How many significant digits are there in this number? Pop quiz. You've already answered. You've already answered. Somebody else? 2. Are you sure? Not necessarily. Right? Normally, right, this is again one of those insidious things, right? Anybody else have another number other than 2? You've already answered. 4. Right? If it is 1500, then it is actually 4 significant digits. Almost always, you're right. Right? In virtually every single case, if you look at a number like this, right? Like there is 1 significant digit and it's the 1 in front, right? Technically, that might not always be true. It might actually be all of these going down all the way here, but it's almost like engineering discretion, to be entirely honest, and practicality of that. Okay, so let's dive into this stuff. So engineering notation, the terminology for this is mantissa times 10 to an exponent, right? I would never expect you guys to memorize this sort of stuff. If it does come up on multiple choices, then you generally have your open book. Actually, for midterm and final, it might pop up there too. So just, I don't ask you guys to memorize very much. Mantissa is the part in front. Exponent is the exponent. There you go. Mantissa is the part in front, right? And then the exponent is the part inside it. What kind of number is the mantissa? Somebody, you've already answered. Not quite. The entire thing is now afloat. Pardon me? It is decimal, but what type of data type is it? Yeah. Nobody else? More. More than that. What family of math is it? We just covered it. Right? It's nominally a real number. It's nominally a fraction. But if you assume that the first decimal point is right after the front digit, you can actually make it an integer. Right? And that part is nice because integers don't suffer round-off error. So, oh, I'm jumping ahead of myself a little bit here. Okay, what type of number is the exponent? That one's an integer. That one's very obviously an integer, right? But the mantissa can also be made into an integer by convention, right? The process of doing this engineering notation, having the decimal after the first digit, means that you can assume that moving forward. You don't need to write out the decimal anymore. In the algorithm, anyway. Okay, blah, 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 blah. Some examples here. 0 converts to 0e0. I think this is actually a convention. I think technically this shouldn't be the case. Floating point binary. Okay, the exact same thing applies to binary, right? It would be mantissa times 2 to the power of your exponent. And this guy, now you shift over the decimal point, exactly the same as you would do, just in a different number base, right? You would move the decimal point over. You would multiply it by 2 to the power of something, right? And then you would represent that exponent. 5 is 101. And now you've got this thing in binary, which is kind of neat. Binary floating point. So given that the decimal point is always going to be after the first digit, given this type of number, we can now represent floating point binary numbers, right? If they had infinite range, we could always do infinite. But in general, this is again by convention and standard. There's nothing mathematics about this. It's all convention, right? For the single precision variables, we have a total of 32 bytes. We now have a sign bit, right? Because engineering notation can't go negative. So you need a negative sign out in front to denote the sign. So you get a 1. You have 8 to represent the exponent. And then you have, and these are all binary numbers, right? And then you have 23 in the mantissa. Similarly for double precision and quad precision. Okay, so how would the number 0.1 actually be stored? And if you convert it to floating point precision, you get this funny guy. And this is I'm forcing it to write out this 0.55F. 0.55F means 55 digits of behind the decimal point, right? And if you represent that, you can see that when you give the computer the number 0.1, because of that round off error, when you convert it back to decimal, you actually get this, which is, again, a little bit funny. When do you have to worry about this? These errors are called round off errors. As we said before, because you're literally rounding to a certain depth of precision. You're rounding to a certain precision, right? The round off error is the difference between the true and the finite precision equivalent. It can be mitigated by increasing the precision at the cost of computational expense, right? And memory storage. So if you have 100 single precision variables, single precision nobody uses anymore. Now they're all double at least, right? If you have 100 double precision, each one is 64 times 100. If you do quad precision, that's going to be twice as large just for representation. But also the algorithms are going to have to work with all those extra things, right? And the algorithmic efficiency, we're going to talk about complexity. I think we get into that next. I think that's next week. We're going to start talking about that one. It generally goes up by powers. So if you increase the from double to quad precision, you're actually going to increase the processing time for those algorithms by a factor of 2 to the power of something. Generally speaking, like imagine you're multiplying those two numbers, right? You increase both of those numbers, your complexity actually goes up by 4, right? Which is bad. For those of you who have been working with PETSI, for example, through Moose, Bison, Phoenix, Firedrake, anything like that, you can assemble the entire code in quad precision. But nobody ever does that unless you really need it, because the computational expense just goes through the roof. Originally, back in the day, everything was single precision, and then computers went to transistors instead of vacuum tubes. So that's why kind of double became the norm. Okay. When do we have to worry about this? When we have dramatically differing magnitudes of numbers. Since the finite precision, since you have engineering notation, and yes, it's flexible, right? But you're inherently losing a bit of precision in the bigger one. And you can imagine that if your second number is inside the noise of the larger one, right? You're going to lose that. It's going to get lost in the wash. So you cannot rely on the associative properties of addition. If you have what is -1 plus 1 minus 10 to the minus 20, right? What is that number? Somebody give me the correct number. You've already answered. You've already asked too. Somebody who hasn't said anything. Have you already? I go for it. 1 minus 1 plus 1e minus 20. 1e minus 20, right? Computer-wise, the computer does say 0, right? Which is yes, right? So if you bracket it, right? You guys all remember BEDMIS. I learned PEDMIS. I think PEDDAM something is, everybody has, I'm surprised by how many acronyms there are, but anyway, right? Order of operations, right? If you bracket it and you make it do this stuff, what happens here is that the 1 plus 1e minus 20, when you convert that to the floating point representation, that 1e minus 20 gets lost in the wash, right? And 1 plus 1e minus 20 is, in finite precision, exactly 1. And then you subtract 1 and you get 0, right? If you group that differently, which shouldn't matter, right? Associative addition should be associative, right? It shouldn't matter, but in numerics it does. Okay. Generally speaking, compilers are now smart enough that the simplification step will identify this and will kick it out for you. So generally speaking, you don't really see this anymore. However, if you're doing a lot of numerics, like for example, COMSOL, right? Or any of these other things, any kind of, probably in quantum too, I imagine you guys would have this sort of stuff, right? Like generally what you want to do is you want to represent the difference between some kind of baseline, because that baseline can be large. So say, for example, you're doing thermal fluctuations, right? Your room temperature is 273.15, but you only have like, I don't know, you're doing laser pulse diffusivity measurements. Your actual pulse is only like 0.1 degree. The correct answer numerically is to ignore the 275.13. Just subtract that and just calculate the difference from that reference. And it's good practice in general. Anything that you can eliminate like that, it goes into a concept called non-dimensionalization too. It's nice to kind of remove those, because then you're not carrying around all these big bulky numbers, and it increases the precision, right? Because if I'm tracking as a temperature 273.16 over here and 273.15 over here, right? Like the computer is paying attention more to the larger numbers than the smaller numbers. If instead you say 0.01 and 0, now it's paying attention to the correct like precision, right? Generally speaking, you won't see that one, but this one you definitely will see, although hopefully it's going to be hidden from you. Subtractive cancellation happens when two nearly equal numbers are subtracted, which drops the number of significant digits dramatically. So 275 or 273.16 has 5 significant digits. 273.15 has 5 significant digits. First minus the second is 0.01, right? Which has 1 right at the end. That shifting, because floating point precision is tracking that accumulation and that movement of significant digits, it's going to cause you grief, because it's too busy paying attention to large numbers to care about the little ones. Let's see. So if we say, and this is kind of one of these quintessential examples, right? So we have, we convert this to float 32, single precision, blah, 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 blah. This is 9 after 1, 2, 3, 4, 5, 6, 7, 8 decimal places, right? And we do the subtraction, and then we read out what this looks like. This is a representation of this guy, and that looks pretty good. But you see that this digit should be a 9, right? That's what we told it to do, but it's not representing a 9, because this is the floating point finite precision equivalent. This guy down here should be 780, but it's not that either. And when you do the subtraction, you're going to get something which is definitely not right, right? And this is just sheerly a property of this subtractive cancellation. Where does this crop up? Binomial theorem, right? Everybody likes to solve quadratics. It's one of these elementary operations. Negative b minus square root of blah, blah, blah. If b is much, much greater than 4ac, you have negative b minus b and change, right? That's an issue with subtractive cancellation, because now you have negative b, now you have b minus b plus a bit, and you're into this kind of like danger zone, right? Similarly, we're going to talk about finite differencing, but the concept is fairly basic, at least at this level, right? Any kind of rate of change, t final minus t initial, 273.16 minus 273.15, right? You throw that into COMSOL, it would give you a number. You wouldn't necessarily subtract off the constant, right? That's going to be a problem with subtractive cancellation, though. COMSOL is smart enough that it understands that there's this reference, and inside the internal algorithm, that's being subtracted off before being operated on, right? But even just something as simple as final minus initial, like, is already having this problem. again, this like kinds like it kind of sounds like small beans. Like, come on, are we really like paying attention to this sort of stuff? A lot of this has been dealt with under the hood by numerically stable algorithms. Numerical stability is we're going to talk about. It's remarkably big. It's a big catch-all. But one of the components of numerical stability is that you don't have to worry about your finite precision representation. The algorithm itself is more stable to those sort of variations than we would be by paper and pencil if we were doing this by hand. Any questions on this before my 10 trillion seconds exercise? No? Okay. Excellent. So Monday, I'm still working on your tutorial for to get some Python and GitHub introduction in there. They haven't replied to me as of yesterday, so I'll poke them a little bit today. We are going to have our first comprehension quiz on Monday. It will be it's ready to go for that one, right? So stuff like just so you guys know, again, unlimited attempts, work in a group, you know, just at least try it. At least think about the answers. That's all this is supposed to be, and like you're going to get the marks no matter what, as long as you actually try it. It'll go through on A2L, but it's the sorts of questions will be something like, what is the maximum number that you could represent in quad precision, right? And I don't care about the actual number. The multiple choice answers are going to be like 2 to the power of 17, right? It's not 2 to the power of 17, right? It's not 2 to the power of pi. Right? So like, it's that kind of level of like, hey, okay, that's what he's talking about. Okay. What important event, anybody questions? No. Good. What important event happened approximately 10 trillion seconds ago? Don't convert it to years. 10 trillion seconds, right? 10 trillion, 1 followed by 13 zeros. Shout it out. Y2K. Okay, that's one. Big Bang. It's another. Ooh, good one. Okay. Anybody else? Come on, spitball it here. What does your intuition say? Which one? Y2K? Oh, the meteor? Okay. Yeah. Anybody else? So I read this book called Numeracy. It talks about like how like we kind of like throw around these numbers, but we have no conception of how big these numbers actually are. Like 10 trillion seconds, everybody knows a second, right? But like this is kind of the case for engineering notation and unit conversion, right? 10 trillion seconds is around 300,000 years, which is Homo sapiens. Man stood up 10 trillion seconds ago, right? But there's this massive difference. Like we have no conception of this stuff. People are like, anybody ever heard of a mole? Right? Like we have no idea how big these numbers are, how absurd these statistics are, right? I had answers that breakfast. Somebody said that they had breakfast 10 trillion seconds ago, right? And like Big Bang was what, 13.8 billion years, right? No, right? Like I think the dinosaurs were what, 120 million years ago? I would only know that from, was it 66? Okay, there you go. Right? Like it's just all over the place. So this is like the value of like floating precision, stuff like that. All right, that's all I got. See you guys. So today we're going to talk about quantifying error. We talked about round-off error a little bit yesterday. As a reminder, because we only have a finite number of digits to store our numbers in machine code, we have to truncate that. Basically, I shouldn't say truncate it. We have to say round it, and I'll tell you why we shouldn't truncate it. What we want to do now is talk about like how we actually quantify this, because obviously it's a big problem and we need to control it. Okay, so the true absolute error is the first one that isn't actually so practical. None of the true ones are, but you'll see why. The true absolute error is the absolute difference between the real value and the approximate value, right? Pretty simple enough. Anybody know why the true anything isn't really so useful? Yeah, if you knew the true number, why are you bothering approximate it, right? So, but it's still useful to understand at least what's happening with your algorithm, and then you design your algorithm past that. We'll talk about that with Taylor series, actually. So as an example, what is the derivative of sine x at x is equal to 0? Somebody want to jump up with what is the derivative of sine x at x is equal to 0? 1, right? Derivative of sine x is cosine at 0, it's 1. Okay. I'm jumping a little bit ahead here. We're going to talk about forward difference and finite and central difference methods. But the idea is actually really easy, and if you've done any kind of calculus, you remember limits, right? Your final minus your initial over the change, right? That's called the forward difference method because you're looking forward in space, right? So the true value is cos of 0, that's 1, right? True value is 1. And the approximate is whatever that sign is plus a little bit minus the sign at the original point, so sine 0, divided by delta x. And for a particular delta x, and this is a choice, of course, generally it's related, if you're doing differential equations, it would be related to your mesh size. For example, finite element actually works a little bit different. So take that a little bit with a grain of salt, what I just said there. Okay, so if you find that, then you're going to find the approximate value is about 0.99833, right? Of course, that is going to shrink as you get smaller and smaller and smaller, because that's literally how a limit is defined. But you cannot actually calculate infinite. Why can't you calculate infinite? Actually, this is a good one. Okay, so given that, right, the smaller my step size, the more accurate my answer, why don't I use 10 to the minus 20? Or whatever, 10 to the minus 100, 10 to the minus 1,000. You got it. This is the round-off error coming back to haunt you, right? Okay, and then the absolute error is literally the difference, and you see that it's a small difference. Great. Okay, true relative error. Oftentimes, the absolute error is not as useful as the relative error. The relative just means literally the true error over the actual value. A good example for that one is in a GPS. Because if you were looking at a GPS trip from here to Ottawa, you know, it's what, about 500 kilometers. You don't really care about 1 meter difference, right? You're kind of okay. Is it plus minus like 3 kilometers, right? But if you're driving in the car and your GPS is off by 2 meters, well, you just got on the wrong lane to get off the highway, right? So the relative error is sometimes more useful than that. Oftentimes it's expressed as a percent, just out of convenience, to be honest. What's the relative error from the previous calculation? You've got your true error divided by the true value, right? And you get something similar. This is actually kind of a bad example. I apologize. Since the true value is 1, the absolute error and the relative error almost are exactly the same. So I apologize for that one. I should come up with a better example. Generally speaking, we won't have the true error or the true value. If we did, what's the point of the approximation? So instead, we talk about the approximate absolute and relative error. Pretty simple. We just take the better approximation, which in this case is the step size, smaller step size, minus the larger step size divided by the better approximation, right? And what we end up getting there is something that kind of looks like this. As you get smaller and smaller step size, yes, generally you will get a more and more accurate number until you hit a precipitous drop. And all of a sudden, it literally just runs off a cliff because floating point error kicks in, and now you have this problem. I'm getting ahead of myself here. I just gave you guys the answer later. Okay. Since we don't know what the actual value is, how can we ever, like, say that this number is good enough? Right? Because I could keep taking a smaller and smaller and smaller step size. At what point would I be able to say algorithmically that this is good enough? Anybody? Friday morning, you answered the question. Yeah. Okay, I'm going to go with, you guys are quiet over here. Don't make me pick somebody. Pick? It's tolerance, of course it is. What does tolerance mean? Yep. Exactly. Yeah, that's exactly it. It's you cannot say that anything is ever correct in numerical methods, period. Oftentimes you can't say that in analytics unless it's very restricted cases, but generally what you want to say is that I can't do any better, which is not really the same thing, but that's what we've got to work with. The way that you quantify that is through the approximate error either the absolute or the relative tolerances, right? In this case, it's kind of funny because sometimes the relative tolerance, like the magnitude sometimes gets swapped depending if you're going for like a large number with small changes or a small number with large changes. If you're going for a small number on the bottom, like if your answer is okay, so let me come up with a better one than that. Say my real answer is 100, and I've got an approximate method that's going in from 89, 90, 95, 98, 99, right? Your absolute error is going to be 1 on the last one, 98, 99, over 99, which is relatively small, right? So that one might trip over your absolute tolerance. But your relative tolerance, right, can be, what is it? Sorry, I'm tripping myself up here. Need more coffee. No, sorry. Your absolute tolerance is just 1 because it's just 99 minus 98, right? Your relative tolerance can be 99 minus 98. That's 1 over 99, which is about 0.01. So your relative tolerance is already pretty low. But if you're going from the other angle, if you're going with a small number, say your answer is actually 0, right? And you're like 0.1, 0.09, 0.08, so on and so forth. Because of that reciprocal on the bottom, because of your decimal on the bottom, your relative tolerance actually becomes the larger of those two quantities. So your absolute tolerance becomes like 0.01. Your relative tolerance becomes 0.01 divided by 0.01, which is 1, which is the larger one. So if you're just doing like a vanilla kind of tolerance, hey, when the tolerance threshold drops below, 5%, or not 5%, like 0.01%, something like that, right? Sometimes it'll be your absolute tolerance that trips that level. Sometimes it'll be the other one. What that means is that you probably want a more intelligent algorithm, right? You want something that's going to be watching your absolute tolerance or your relative tolerance, but both are actually useful. It's kind of tempting to think, well, relative tolerance is obviously the right one. It's not. You kind of need both. Here's a fun one, right? Let's explore that derivative, the tolerance in that derivative calculation from sine as a function of the step size, right? So as we get down to a step size, the answer should get better and better and better, right? If we do this, we're plotting this on a log-log, we get this plot here. Anybody know why the curves overlap? I already gave you guys that answer. Yeah, since the true answer is 1, the two are that, and I should come up with a better example. Okay, plots a straight line on the log-log scale. What does that imply? Right? It implies a mathematical structure. Actually, I put that one in just to raise a little bit of awareness. Whenever you put something on a log scale, logs tend to distort like any little differences, right? So even though it looks like they're overlapping on log-log, if you did that on a linear scale, you would actually see a bit of that difference there. Right? There's a sharp drop-off around 10 to the minus 8, right? Nice, straight, flat chunk. What does it drop off? Okay, back row. We got 1, 2, 3, 4th person over. I see you. What's the drop off? Why does it drop like that? Take your guess. Max error? No. The error is what we're calculating. Anybody else? I'm going to pick somebody else. 1, 2, 3. Tolerance? No, not tolerance. Yeah, I'm going to keep going. Row back there. Got 1, 2, second person in. Yep. No ideas? No ideas? Green shirt already answered it. It's the round-off error. This is what happens. It gets smaller and smaller and smaller, and everything is nice and hunky-dory, and everybody's happy. Then all of a sudden, you drop below that precision. Look what happens here. This is around 10 to the minus 15, 10 to the minus 16. That is the decimal equivalent of floating point double precision. right? 2 to the power of whatever it is in the exponent. It comes down to about 10 to the minus 16. Generally, if you see any numbers in a computer code that is 10 to the minus 16, typically that means 0. And the reason is because of this, because of the floating point precision. You might think 10 to the 16 is 2 to the power of 4. It's not, because it's in binary, and binary is the way it's machine represented. Anything 10 to the minus 16, like rule of thumb, basically 0. Any questions on quantifying errors? Okay. Truncation error. Remember how I said this course is basically linear algebra and Taylor expansions? We're into Taylor expansions. All right. Truncation error is because approximating mathematical function is typically done by Taylor expansions. There are problems with that. We'll see what they are. Right? Everybody's done Taylor expansions. Okay. You'll be doing Taylor expansions for the rest of your life, honestly. They're just massively, massively powerful. Okay, here's the equation. Everybody should know it. We cannot compute an infinite number of terms, right? Everybody knows that at this point. Okay. If delta x is small. Do you guys remember in expansions, when I learned Taylor expansions, back in my day, we talked about zones of convergence and convergent series. Do you guys talk about convergence and series and regions of stability and things like that, right? Everybody like kind of think, okay, guy, like, shh, Taylor expansion, right? Like, guess what? This is where it comes back and haunts you. The idea is pretty simple, though. If delta x is small, then the higher order terms become progressively smaller. Then you are in the zone of convergence, and then you can use this without having an infinite number of terms, right? And therefore, we can truncate it. We can cut off this series after a certain point. Now, the truncation error can be calculated effectively analytically. And we're going to be using this a lot. This is all of the stability issues of like differential equations, implicit time steppers. You're going to see all this stuff comes back, right? This is an example where having the analytical expression and having the true answer is actually useful for like analysis of this sort of thing. Okay. Here's the equation depending on where n is, right? Typically speaking, you know, we have the analytic expansion, but it's almost not really useful, because you don't know exactly where you are. You might not have the exact analytic, blah, 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 blah. Notice that your parameter, in this case, your step size, is being raised to a higher and higher power as your series expands, right? Here it's raised to the power of 0, 1, 2, 3. This is a third order expansion. Everything past that is higher than 3. Typically, what you want to use is, did you guys cover big O notation? Okay. Big O notation is a way to describe the error linked to the power of your parameter. So if I want to approximate, if I ask the computer what is sine of x, it's not going to calculate the trig function. It's going to go off and do a Taylor expansion, right? It's going to do a Taylor expansion to varying degrees of x. Right? And my game is to say what order of precision is that approximation. And that order relates to the step that I'm using in that approximation. Okay? I don't actually say what is sine of x. Technically, it's sine of x minus 0, because sine of 0 is known. So you're actually doing a Taylor expansion about that. Yada, yada, yada. If you are doing something like this, so in general, when you're doing Taylor expansion of a function, and you know your x naught, right? You know your starting point. You want to find x naught plus delta x, right? This is your equation. You've got f at x naught, f primed x naught times delta x plus f double primed x naught delta x squared over 2. Let's cut it. And we say that everything else is on the order of delta x cubed. What happens when you have delta x? What happens to your error? Anybody? I'm going to go over to this side next. I'm telling you guys right now. If your order, like, take a look at this, right? if I'm only calculating 1, 2, 3 terms, if I am then having delta x, how does my error change here? Second row from the front. What do you think? Yeah, you. Yeah. I don't like to just like point. Yeah, you. Yeah. You tell me. Well, go up because the smaller the step size, the better, the higher accuracy it's going to go. It'll go down. How much? 3? Okay. Any other thoughts? I'm going to just go back in rows. So somebody wants to throw a pie in my face. Yes. By the exponent 3, what do you mean? If I have the error. Not factor. You were right. You were on the right track with the exponent, right? What happens is that because the order is on the order of step size cubed, if you take half of that, it's going to reduce the error by roughly a factor of 8, right? Half 2 to the minus 1, right? Cubed 2 to the minus 3 is 1 over 8. If I were to reduce it by a factor of 10, that would roughly reduce it by, improve the error, reduce the error, thereby improving the answer by a factor of 1,000, right? This is the sort of thing that you want, because at the end of the day, you're going to have to say like, hey, I want to calculate this finite difference. How small does the step size have to be? Ideally infinite. We're never going to get to infinite. Ideally as small as machine precision. Right, that's kind of the other go-to. Hey, if things don't work past 10 to the minus 16, let's just use 10 to the minus 15, right? That's wasteful, and you're still prone to error. But if you can do this sort of analysis, you can say that this is good enough. This is the point of diminishing returns, right? And the higher order accurate your method is, the faster you get to that accuracy. This is the game. This is the game of numerical methods. Effectively, it is the leading term of the rest of them. Not even the leading term. It is quasi-analytically, I would say. So consider your whole Taylor expansion, right? If I just wanted to use a second order expansion, I would only have these 3 terms, right? 1, 2, 3. I know analytically what the error is here, right? The error is defined as this one plus this one all the way sum to infinity, right? So I could say that that error is that term. But because we're in the world of approximations and gibbledy-gobbly whatevers, instead what we actually care about is the power of our parameter. And our parameter in this case is delta x. So what you do is you take everything past that point of approximation. You only care about your leading term, your highest order term, and you say that the constants don't matter. And what you get is some order of delta x to the power of 3, which means that there are other terms too, but they're all smaller. So as long as delta x is small, then that is the leading term. Nobody cares about the constants because constants come and constants go, right? All that they really care about is the change as you're changing these things. Okay, this is a fantastic example of how this sort of thing works and what this art is all about. So we talked a little bit about forward difference approximation for the first derivative, right? What you do is you take your known value, you take a teeny tiny step ahead of it, you find those 2 values, you divide by the step size, and you've got your derivative, right? Make sense? Excellent. Turns out that that's bad. Okay. What you're going to get if you look at this expression compared to your analytic expansion, right? So what this is actually the first 2 terms of your Taylor expansion. And if you do the Taylor expansion, you're going to get this plus this guy, right? Yada, 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 yada. And you're truncating off everything past this guy. Do you guys see how that works? Should I write it out on the board? I'm gonna write it out on the board. Okay. What have we got? You've got, so f at x plus delta x is equal to f at x, sorry, x naught. Okay, f at x is equal to f at x naught, some known value, plus, wait a second, I'm calculating primed, sorry. Dun, 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 dun. How does this work? F at x plus delta x, no, I was right the first time, is equal to f of x plus, what is it? F primed at x delta x plus f double primed at x over 2 delta x squared, da 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 da. You guys see that one okay on the side? Okay. If this is what we want to find, right, we can rearrange this series. And what we're going to get is f primed at x is equal to this guy, f at x plus delta x minus, oh, sorry, this should be minus there. No, that's right. Minus f at x over delta x, right? Because the delta x comes through. Is this okay, or you want me to go through more details? I'm gonna drill in a little bit. This is the name of the game here. So it's important that you get it right. So this guy moves over to this side. You have this minus that minus f double primed over 2 delta x squared da 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 series. Take this delta x and divide through everywhere. F primed at x, f at x plus delta x minus f at x over delta x, right? And here's the tricky part. Minus f double primed over 2 delta x da 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 da. Because this guy ended up getting divided through by delta x. That makes sense? So you've approximated this guy is approximately f x plus delta x minus f of x all over delta x minus this guy cancels, and you've got O delta x. Forget about all the constants in front. You've just got that order of blah, blah, blah. That's what this guy is saying. Everybody with me? Yep. Yeah, so f double primed is just a constant. This is f double primed at x at some known value, which doesn't change, right? So it's just a number. It's a constant, and we don't care about constants. Yeah. So if for example, you were to try and get a better approximation, right? What you would do is you would change delta x. F double primed at x hasn't changed, right? All you're changing is that parameter. So anything that doesn't change with that parameter, forget it. And all you've got is that order. Does everybody understand how this became order of just delta x and not delta x squared? Right? Because of that cancellation. That's where the magic happened. Okay. Since the error, which is this term here, is on the order of delta x by itself, not squared or anything like that, this is a first order accurate equation. Right? Literally first order as in polynomial to the power of 1. Okay. Anybody confused before we go on? Yeah, shoot. This guy. From the second term of the Taylor expansion. Yeah. Right? Because you've got f, you start off at, so you're assumed to know like this value here, f at x, and you say, well, okay, f at x plus delta x is f of x plus the derivative, which turns out to be what you want, times that delta x, plus second derivative, blah, 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 x squared, et cetera, et cetera, et cetera. And then you take that series and you rearrange to isolate for f prime. Okay? Yeah. Just try it out. Like try doing the paper. I should bust out the derivation here a bit more. Okay. Nobody does forward difference. Yeah. Oh, what does that actually give you? What if I wanted a better answer? How would I get a better answer? Yeah. Well, okay. So if I have to use forward difference, if my hands are tied and forward difference is the only tool that I have in my belt, right? But every time that I make delta x, every time that I cut delta x in half, my error only reduces by a factor of a half, which is okay, but it's not great. We can do a lot better. Exactly that. Exactly that. The order is telling you how much your answer improves when you tune that parameter, right? But not, sorry, no. It's not telling you how much it improves. It's telling you the factor by which it improves, right? So let's move on to central difference, and then it'll become a lot more clear, okay? If instead, what we did, instead of taking what, the derivative at this point, need more whiteboard. Anybody who's been to my office will realize that I have like the biggest whiteboard I could find. Originally, I was just going to paint the entire walls, but apparently it has like super high VOCs, and I figured I probably shouldn't cause like an evacuation of the nuclear research building in like my first day there. So, especially because of like chemical something. Okay. Forward difference basically says we know f at x, and we want the slope there, right? So what we're going to do is we're going to take another value over here, f at x plus delta x, right? The other thing that you could do is go backwards. Exactly equivalently. You could just take a step backwards, and you could do basically the same thing using f at x minus delta x. And that's called the backward difference, right? Literally forward, backward, not exactly rocket science, okay? Actually, it is rocket science, but anyway, very elementary rocket science. Anybody know what would be the order of accuracy of the backward difference? It would be exactly 1. The mathematics is exactly the same, right? Because the order doesn't care about those constants. -1 is a constant. Everything's fine. The magic is when we do this Taylor expansion, and we can actually do it pretty easily, what you do is you take, what we're going to do is we're basically going to average the two. We're going to take our, hold the thought. We're going to take our forward difference, which was, let's see. Just got to make sure I'm getting this right here. F primed at x is equal to hold on a second, I got to make sure that the math is right here. Yeah, okay. I'm just going to resort to this one because the negative signs turn out to be important. Okay, so what you do, this part here is the forward part. You've got f of x plus f primed of x delta x, right? Plus f primed of x delta x squared. And you're gonna average that. So you're gonna take that, put it together with the backward equivalent, negative f prime delta x. The negatives cancel out in the Taylor expansion because you're squaring it. And you got this positive term again. And then you get divided by, oops, twice that distance. So you've taken your forward one, you've taken your backward one, you've averaged them, and what ends up happening is that that f double prime term cancels out. Which is kind of funny, and I think I should probably show this on the board. Yeah, hold on a second. I hate doing live demos. Live demos never work. Here we go. So we already showed f primed at x was approximately equal to, what was it? F at x plus delta x, this is forward difference, right? Minus f at x all over delta x. Everybody remembers that part, right? Okay. And then I think this was minus f double primed delta x over 2. So far, so good? Okay. And then there were other terms. This was f triple primed something, right? This would be delta x squared, so on and so forth. Blah, 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 blah. So far? Okay. Swap out delta x with negative delta x. And you can do that. Just take delta x. Now it is negative delta x, right? So this is forward. Backward turns out to be f primed of x, f at x minus delta x, minus f at x. It's a lot of math, but like do it and it shows out. What happens to this term? Becomes a negative sign, right? Because we've swapped x for negative delta x. This becomes plus delta x, still delta x. This one doesn't, right? Since this one is squared, this actually becomes 2f triple primed delta x squared. And then you also get some of that cancellation, funny business over here, but nobody really cares because this is going to be your leading order term. Okay, so now we've got, yeah. Oh yeah, sorry. No, you're right. I bet. Okay. What you've got now are two different but equally valid approximations for the slope at x, which is what you wanted, right? But how can it be both? Well, chances are it's not both. What do we do when we have two different options? As engineers, we average, right? So we can say that f primed central is equal to f primed forward, right, plus f primed backwards, all divided by 2. When we do that, what we're going to get is f at x plus delta x. So let's take this negative and put that in there, right? We've got that guy minus f at x, and then plus this guy, which turns out to be negative f. Tell me if you guys aren't following this, by the way. Minus delta x plus f of x, all divided by 2 delta x. So far, so good? Add on the error terms. This guy is exactly the negative of this guy. And this is the magic. Analytically, they are the same. Delta x plus f, blah, blah, this turned out to be, oops, delta x squared, that just adds, right? Because it's just the same there. These guys cancel out. These guys minus f of x plus f of x also cancels out. And all you're left with is f at x plus delta x minus f at x minus delta x all over 2 delta x plus order of what? I see one answer here. You guys at the back, how about the long row there? How about second in? What is the order of this approximation? What's that? 2? 2 it is, right? This is now because the leading term of the surviving expansion over here is delta x squared. Therefore, this O is delta x squared. Okay? This is a central difference because you're literally taking the one ahead and the one behind, dividing it by twice the difference, and you've got a better answer, a quantifiably better answer. So in this case, if I were to half the step size, if I were to get it like half the size, what would happen to the error? Right? It will go down by a factor of 4, right? 2 squared, factor of 4, right? Which is better, quantifiably, mathematically better approximation. Central difference is the way to go. Note, we have not called the function, right? Sometimes these functions are costly to call, right? We haven't called it any more times. This took 2 function evaluations, 1, 2 divided by that step. This one takes the exact same number, 1, 2 divided by the step, but we've got a mathematically better answer, right? This is the magic. This is the magic of all these methods. You got a question? Oh, yeah. Huh? Excellent. The math is here. I just skipped a whole bunch of steps in the middle, apparently. Sorry. Yeah. It's only the leading term. Because everything is typically within the zone of convergence. The later terms contribute less and less and less. By definition, for a convergent series, the higher order terms contribute less and less and less. But let's move on and we'll talk about that one. Common mathematical functions, in case you don't know what Wikipedia is. Examining the terms of sine. Okay, so here's where the funny business comes up, right? Let us calculate what sine of x is to a varying number of parameters, right? So this term, first term within the Taylor series. Okay, let's calculate it to 10 terms. The first term for sine of 1 is 1. The second term, that whole like f prime divided by what? In this case, it would just be f prime. Second term would be f double prime divided by 2, right? Third term would be blah, 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 blah. On and on and on, right? Notice how these are getting smaller, right? First term is 1. Next is negative 0.16. Yeah, and you've got 2 zeros, 3 zeros, 4 zeros, right? You are in a convergent series. For larger values of x, the terms initially grow very large before they start to converge, which is kind of funny, right? So if we do the same thing with sine of 10 instead of sine of 1, well, we're going to see that the first term is 10. Second term is negative 166. Third term is 800. Fourth is 2000, right? We hit almost 3000, and then it starts to converge, which is also kind of funny, no? Right? Like just because you're doing sine of 10 instead of sine of 1, just because that value is different, what you're actually doing is you're expanding around 0. Everybody knows what sine of 0 is. It's 0, right? So the difference between sine of 0 and sine of 1 is a step size of 1. The difference between sine of 0 and sine of 10 is a step size of 10. And now your step size is becoming massive. It does converge. It does. But it gets terrible before it gets better. Getting ahead. Don't read ahead. Don't study beforehand. Inquisition-based teaching and learning. There we go, right? So if after 10, right, you were to calculate the approximate value of sine of 10, right? You would get that compared to the actual value, which is actually pretty different, right? And that's because you've gone up before you've gone down. You would need to keep going and going and going before eventually you would recover the real answer again. It would eventually get there because you have crossed this zone and you are now converging, but you would need a whole bunch of terms. You can't just use 10. I have no idea what the computers actually use. That would be an interesting thing to know. For very large x, the approximation is completely wrong. So if we were to ask for sine of 100 and just naively apply the Taylor expansion, what we would get is this guy. 100, what is that? 10 to the 6, 8, blah, 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 right? And you've got this massive guy, right? And at this point, you're again running into round-off error, right? So you're never going to converge. Even if this thing did come back down and did start to level off and you did re-enter the zone of convergence, it doesn't matter because you're so big that changes over there are not going to be large enough to contribute to the finite precision, right? And sine of 100 is in fact negative 0.5, not, I don't even know what that is. 8 Google. Okay, what does this mean? How are we supposed to do this? Because you can't for sine of 100, and it will give you the right answer. Right? Which comes back to your question of, so what are we actually supposed to do here? Anybody? You answered one. Only one question. I'm going to go for the back row. Warning you now. Okay, left side at the back, please. What would you do if you were asked to calculate sine of some large number? And you knew what sine was. Anybody else? I'm going to move forward. You already answered one. Okay. Next row in. You too? Tim Hortons cup, bag on the side. I apologize by naming you guys according to whatever's on your desk, but that's all I got. The alternative is to have name tags. I don't think anyone wants that. Tim Hortons cup. What kind of function is sine? Yes. So what does that mean? Right? The Taylor expansion itself has problems, but because we understand about what the function is, we could implement that. We could put that into the algorithm for calculating these things. We can reduce that, we can remove that periodicity and bring 100 to whatever, some factor of 2 pi plus modulo whatever, right? And now all we actually need to do is that modulo or whatever, right? I don't know what factor of 2 pi goes in there. Doesn't really matter. All this comes back to why we should use a package. This is exactly what the packages are, right? They're people smarter than us, especially myself, maybe not you guys, right? I've been working on this stuff. They understand how this sort of stuff works. It makes it simple, but it also makes it robust, because if you were just doing Taylor expansion, you could be forgiven by just taking it up to 100 and not realizing that it was giving you terrible answers. And if you put that sine value inside some other function and you didn't see negative 8 bazillion here, you wouldn't necessarily see that, right? All you're going to see is that your COMSOL crashes. Not very useful. Frankly, this is why I think the packages are superior to any kind of AI generated thing, because AI might know this, the packages definitely do. So if you have the option, use them. Another very insidious one that comes up a lot is actually the exponential, exp of x minus 1 when x becomes small. It becomes a whole bunch of problems. And it's because the expansion of this becomes the exponential of x is roughly equal to 1 plus x, right? As x gets very small. When x gets small, this tends to get washed out in finite precision, because you've got 1 and you've x over there. That tends to cancel out. You get that subtractive cancellation problem. So a lot of functions will implement exp m1. And I think that there's a corollary for ln. I think it's ln p1, right? And what that's good for is calculating this exact formula to high accuracy. It's a different Taylor expansion. You're not expanding exp of x, you're expanding exp of x minus 1. And that isolates those terms and brings them more common. I saw this commonly in Excel. This is the first place that I found it. Because in Excel, sometimes what you're going to do is exponential decay. How many people are in 3D04? Right? How many people are already doing exponential decay? Right? Exponential decay is kind of a big thing, right? Especially in radioactivity. And if you go down to close to 0, right? Close to your initial time, you still want a good number. You still want an accurate number, because what that means is that that's your actual radioactivity, right? After the decay half-life, right, you want your actual radioactivity. If you just blindly put that into Excel, you're actually going to get problems because your numerical algorithm breaks down when that time step gets very small, right? Unless you do the analytical one. And honestly, the analytical one is better. But if you're doing that in Excel because you're doing a lab or something like that, keep in mind EXP M1. That's all I got.